Welcome. In this and the next few sessions, we are going to look at our final topic regarding integral, namely improper integrals. When we define the Riemann integral, we assume that the function was defined everywhere in the interval from a to b, including the endpoints, so that all possible Riemann sums are defined. We also assume that f was continuous to ensure that the limit of Riemann sums exists. It turns out that even if f is not quite continuous, limit of the Riemann sums will exist, but we will not worry about those technicalities. But in some applications, we want to relax this a little bit. There are two different things that happen. We are going to look in detail at only one of them. I will just mention a very basic rule of thumb that can be used for the other situation. The second situation, the one which we are not going to look at in detail, is to allow the function f we want to integrate to be discontinuous. It turns out that we can do this in such a way that the fundamental theorem still works as long as the antiderivative is continuous everywhere and the function f equals the antiderivative. But it's possible that the antiderivative is not differentiable at a finite number of points in the open interval from a to b, or equivalently that f is not defined at a finite number of values in the interval. The crucial point is that the antiderivative must be continuous even where it's not differentiable. For example, the integral of dx over the cube root of x squared from -1 to 1 can make sense using this approach, even though the function we are integrating, 1 over cube root of x squared, has a vertical asymptote at x equals 0. Take the antiderivative. Recall, to find the antiderivative of this function, I write that using negative exponents. Apply the power rule, which gives me x to the power 1/3 over 1/3. And then for the definite integral, I'm just going to use the fundamental theorem, ignoring the fact that x to the power 1/3 is not differentiable at 0. Even though x to the power 1/3 is not differentiable at 0, it is continuous at 0 and at every other number in the closed interval from -1 to 1. It's important that the function is continuous even at the endpoints. Now, if the function is not continuous at even a single number in that interval, then the statement is wrong. Of course, if it's not continuous at the endpoint, then also it's wrong. But that's easier to catch because you are looking at the endpoints when you use the fundamental theorem. So for example, the integral of dx over x squared from -2 to 1 does not exist, even though if you carelessly apply the fundamental theorem, it looks like it has an answer. The reason is that the antiderivative of 1 over x squared, namely -1 over x, has a vertical asymptote at 0. In particular, it's not continuous at that number. This is a useful rule of thumb, but it's not the formal definition. The formal definition is more complicated, so we can deal with situations where we don't know what the antiderivative is. But a lot of simple examples where we want to do this kind of improper integral can be handled by this special case. The second version of improper integral is where one or the other endpoints of the interval of integration is infinity or -infinity. This happens somewhat more commonly in the applications you will see, in particular in statistics, and in queuing theory sometimes you run into this type of improper integral. We replace the infinity or -infinity by a variable and then let the variable go to infinity or -infinity, whichever one was in the original integral. To define the integral from a to infinity of f of x dx, we first replace infinity by some variable. I'm calling it r. Take the integral from a to r of f of x dx, where I assume r is a regular number, and then I let r go to infinity. If the limit exists, that's defined to be a value of the original improper integral from a to infinity. If the limit does not exist, we say that the integral diverges. Same way to define the integral from -infinity to b, change -infinity to some variable, r, where r is a regular number, and then take the limit as r goes to -infinity. And if the limit exists, we say the integral converges to that limit. If the limit does not exist, or if the limit is infinite, we say the integral diverges. To define the integral from -infinity to infinity, we split it into two. We take the integral from -infinity to 0 and from 0 to infinity. Take the integral from 0 to r and let r go to infinity. Take the integral from s to 0 and let s go to -infinity. If both these limits exist under finite numbers, then this is the value of the original improper integral. If one or other or both of the limits don't exist, or even if one of them is infinity or negative infinity, we say that the integral diverges and we don't assign a value to that integral. We will look at examples of integrals where the interval of integration is infinite in the next few sessions.